Hi, Yusri here. This video is about the head loss in small bore piping systems experiment of the IEA201 Unit Operations Laboratory course, which is a part of the Environmental Technology undergraduate degree program. Imagine a pipe and there's water flowing through it, and also imagine that there are thin tubes attached to this pipe, and we allow some of the water to flow into these tubes. With these tubes, the water will come into the tubes and it will reach it will not flow out, provided that this flow is not hampered in upstream. This height of water represents the pressure of the water at this point, and this height is for the pressure of the water at this point. As you can see, there is a difference in heights of the two levels due to the changes in pressure of the water from this point to this point. Now, the changes in the height is what we called head loss. Now, the unit of this head loss is simply distance. So, the distance between this and this, if we were to measure it using a ruler, we would get a simple distance value. Let's say we use the example of 5 centimeters. So we can say that the head loss between this point and this point is 5 centimeters. Sometimes engineers use 50 millimeters, which is use millimeters instead of centimeters as a standard. Now, what causes this loss in head? As the water flows down the pipe, the water itself will experience friction and causes it to slow down, which means that energy will be lost from the water into the surroundings or into the walls of the pipe, which also means that it would have a reduced energy level compared to this point compared to this point, and thus the loss in pressure at this point. Now, since this tube is representative of the pressure of the water, thus we call these tubes piezometers. Piezio means pressure, meters would mean to measure or a way to measure the pressure. So these tubes measure pressure, but the key point here is that we don't measure absolute pressure, but we measure the difference in pressure. We can write this as an equation to represent the changes of head or head loss with different pipe lengths. We can write it as delta H or head loss divided by delta L, where delta L is the distance between tube 1 and tube 2. And we call this ratio I, or the hydraulic gradient. This hydraulic gradient is a dimensionless value, but it indicates the magnitude of head loss with distance. So the higher the hydraulic gradient is, the bigger the pressure drop of the water flowing through the pipe. And also, if the hydraulic gradient is large, it would mean that the friction exerted by the pipe onto the water would also be great. There are mainly two types of flow in a pipe. The first is what we call the laminar flow, and the second is the turbulent flow. The hydraulic gradient is dependent on the types of flow. If it's a laminar flow, the hydraulic gradient is directly proportional to the flow velocity to the power of 1. If it's turbulent flow, then the hydraulic gradient is directly proportional to flow velocity to the power of n. This implies that if the flow is laminar in the pipe, then there is less hydraulic gradient or less pressure drop in the length of the pipe. But if it's a turbulent flow, then there is an increase to the factor of n, power of n, head loss due to the length of the pipe. How do we determine whether a flow in a pipe is laminar or turbulent? We use the dimensionless number, Reynolds number, to give us an idea of whether the flow is laminar or turbulent. Now RE is equals to rho U d over mu, where rho is density of the fluid, or in this case water, U is the velocity or the mean velocity of the water, d is the diameter of the pipe, and mu is the viscosity of the water. So from this equation, we see that the higher the U, the higher the Reynolds number. So from experimental work, or the researchers found that if RE is more than 2000, it is most likely turbulent. If RE is less than 2000, then the flow is laminar. So if we want to determine the hydraulic gradient, then we first need to determine whether the flow is laminar or turbulent using this equation. Once we determine that it is laminar, then we can use this relationship, but if it's turbulent, then we have to use this relationship. Now this equation would mean that I is equals to K, a factor, U, while this I is, for the turbulent, I is equals to another factor of U, but to the power of n. So what is K? K for laminar is equals to 32 mu over rho g d square, and for turbulent, K is equals to 4F over 2D G. Mu again is viscosity of the fluid, which is a constant at constant temperature. Density, rho is density of the fluid, which is also constant with temperature. G is gravity, a constant value, and D is diameter of the pipe. D and G here is similar to the definitions above, while F is friction factor, which depends on the pipe that the water is flowing through. Now we'll discuss about typical units or fixtures within a common piping system. So there will be head loss in even straight pipes. This is an example of a straight pipe for the unit that we have in our lab. The straight pipe is there are tubes connected to the straight pipe that's connected to this piezometer for us to measure the difference in height. So there's one tube here and another tube here, and there'll be water inside here, and the difference in water is the head loss. And to refer to what we discussed in the previous slide, we know that the hydraulic gradient is the head loss divided by the difference in length. So the difference in length is this. So we can measure the head loss just by reading the difference in height in the piezometer. But there is also an equation that you can use to estimate head loss, given that you don't have these piezometers to measure the head loss. You've seen this equation before. Delta H is equals to HL, which stands for head loss, and it is the same as delta H equals to 4FL V square. Note that V square is the same as U in the previous slide, which stands for velocity, divided by 2dg. Now, where did this L come from? L is basically from here. Notice that delta before, the hydraulic gradient is delta H over delta L equals to 4F V square over 2dg. So when we bring this L over here, it becomes the length in this side of the equation, which is also which is the same as L here. So if you don't have these tubes to measure the head loss, you can still estimate the head loss using this equation. All you need to know is the friction factor of the pipe, the velocity in the pipe, the diameter of the pipe, and you know this is the gravitational acceleration constant. There will also definitely be some head loss due to sudden expansion of pipe. So imagine water is flowing from here to here. There's a sudden increase in the diameter of the pipe that causes the velocity to drop from V1 to V2. Due to this sudden change, there will be some energy loss or pressure loss because of this sudden expansion. Again, we can measure the head loss by looking at the piezometer attached to these tubes to determine the difference in height, which is the head loss. But we can also estimate it using equation. And that equation is delta H equals to HL equals to V1 minus V2 square divided by 2g. There will also be head loss due to sudden contraction, just like before for the expansion. In the experiment, you'll be measuring the head loss from the piezometer, from these two tubes, and also comparing it with the equation, which is HL equals to capital K V2 square divided by 2g. Now V1 is here while V2 is here, with the flow moving here. So notice that in this equation you only need to determine the velocity after the contraction. Now what is K? K is the dimensionless coefficient, which is dependent upon area ratio. There are different K values for different area 1 and area 2 ratio. So for an example, A2 over A1, and the K value, if I were to draw a rough table right now, if the area 2 to area 1 is 0.1 or 10%, then the K value would be 0.46. If the area is 0.2, the area ratio is 0.2, then it is 0.41. If it's 0.3, then the K value is 0.36. This means if the A2, or the area of this pipe after the contraction, is a lot smaller than the pipe before, then the K value would be higher. And the smaller the difference in contraction or the difference in area, the lesser the K value will be. Which makes sense, because if the K value is high, then the head loss would be high. So you can expect that if the changes in area between the two sections or the two areas are large, then you can expect greater head loss. You can find this table in the manual provided. It would range from 0 until 1. A1 to A2, A2 to A1 ratio. Now, how about bends? There's two types of bends here. One is the 90-degree sharp bend, or what we call the 90-degree meter bend. And there's also this smoother bend. This just demonstrates the difference of the different types of bends used in piping systems. Since all these bends or all these units are attached to piezometers, we can directly measure the head loss from the piezometer. But just like before, we also would like to compare the values calculated using equations with actual values. So we can calculate the head loss due to bends using almost similar equation as the sudden contraction equation, which is HL equals to K V square over 2G, where V is the mean velocity after the bend. In this experiment, you need to determine K for 5 different types of bend and elbow. There are 2 types of valves in this experiment. One is the gate valve and the other is the globe valve. So the difference between gate valve and globe valve is the mechanism within the valve. So for a gate valve, you notice that the obstruction or the valve that is blocking the water from flowing if the tap is closed is designed to either restrict the flow fully or to allow the flow fully. This is for the closed configuration of the valve, and this is for the open configuration of the valve. But for the globe valve, it has a more transitional change in flow rates or in flow that's allowed through the pipe. So once we open or close, or once we open the valve, it would either be there is a steady increase of flow with the degree of opening of the valve, and this is different. This steady increase in flow with the opening of the valve is different than how the flow is allowed through the gate valve. We can also calculate or estimate the head loss of the gate and globe valve using the same equation that you saw before, which is HL equals to KV square over 2G. Now, from the table given in the manual, there are a few K values provided, one for the globe valve and the other for the gate valve. And for the globe valve, K is equals to 10 if it's fully open. And if it's for gate valve, if the gate valve is fully open, K is equals to 0.2, and if it's the gate valve is half open, K is equals to 0.56. So here is the picture of the experimental piping system, which consists of pipes that are small in size, or what we call the small bore pipes. The diameters of around 1 inch nominal size. So water comes in from this side, that's the inlet, and it goes through the system as so, and gets split in this point to go into the light blue circuit that goes from here, up here, down here, and back out through the outlet. And also the dark blue circuit that goes through here, up here, and down through here again to the outlet. It all combines together at the end. And the difference between these two circuits are the valves attached to it. The one in the dark blue circuit is the gate valve, and the one in the blue circuit, light blue circuit, is the globe valve. There are a few units or fixtures, like mentioned before, in this unit. There is the sudden expansion here, the straight pipe from here to here, sudden contraction here, the smooth 90-degree bend of 2-inch nominal pipe size here, the smooth 90-degree bend of 4-inch nominal pipe size here, and the smooth 90-degree bend of 6-inch radius here. Now for the dark blue circuit, there is the 90-degree meter bend here, or the 90-degree, or also known as the 90-degree sharp bend meter. And over outside of this diagram, where this pipe is connected to here, there's another bend, which is the proprietary 90-degree elbow. There is the straight pipe here, which is smaller than the straight pipe here. So this is a larger bore pipe, while this is the smaller bore pipe. So that's it for the pre-lab of this experiment. Thank you.